Greetings to dear friends, thank you for choosing the BigDark channel for teaching scientific content. Please do not forget to subscribe, like, and comment to support the channel. Lidar. Lidar is a method for determining ranges, variable distance, by targeting an object with a laser and measuring the time for the reflected light to return to the receiver. Lidar can also be used to make digital 3D representations of areas on the Earth's surface and ocean bottom, due to differences in laser return times, and by varying laser wavelengths. It has terrestrial, airborne, and mobile applications. Lidar is an acronym of light detection and ranging, or laser imaging, detection, and ranging. Lidar sometimes is called 3D laser scanning, a special combination of 3D scanning and laser scanning. Lidar is commonly used to make high-resolution maps, with applications in surveying, geodesy, geomatics, archaeology, geography, geology, geomorphology, seismology, forestry, atmospheric physics, laser guidance, airborne laser swath mapping, ALSM, and laser altimetry. The technology is also used in control and navigation for some autonomous cars and for the helicopter Ingenuity on its record-setting flights over the terrain of Mars. History and etymology. Under the direction of Malcolm Stitch, the Hughes Aircraft Company introduced the first LiDAR-like system in 1961, shortly after the invention of the laser. Intended for satellite tracking, this system combined laser-focused imaging with the ability to calculate distances by measuring the time for a signal to return using appropriate sensors and data acquisition electronics. It was originally called CoLiDAR, an acronym for Coherent Light Detecting and Ranging, derived from the term radar, itself an acronym for radio detection and ranging. All laser rangefinders, laser altimeters, and LiDAR units are derived from the early calendar systems. The first practical terrestrial application of a calendar system was the CoLiDAR Mark II, a large rifle-like laser rangefinder produced in 1963 which had a range of 7 miles and an accuracy of 15 feet, to be used for military targeting. The first mention of LiDAR as a standalone word in 1963 suggests it originated as a portmanteau of light and radar. Eventually the laser may provide an extremely sensitive detector of particular wavelengths from distant objects. Meanwhile, it is being used to study the moon by LiDAR, light radar. The name photonic radar is sometimes used to mean visible spectrum rangefinding like LiDAR. LiDAR's first applications were in meteorology, for which the National Center for Atmospheric Research used it to measure clouds and pollution. The general public became aware of the accuracy and usefulness of LiDAR systems in 1971 during the Apollo 15 mission, when astronauts used a laser altimeter to map the surface of the moon. Although the English language no longer treats radar as an acronym, i.e., uncapitalized, the word LiDAR was capitalized as LiDAR or LiDAR in some publications beginning in the 1980s. No consensus exists on capitalization. General description. LiDAR uses ultraviolet, visible, or near-infrared light to image objects. It can target a wide range of materials, including non-metallic objects, rocks, rain, chemical compounds, aerosols, clouds, and even single molecules. A narrow laser beam can map physical features with very high resolutions. For example, an aircraft can map terrain at 30 cm, 12 in, resolution or better. The essential concept of LiDAR was originated by Essing in 1930, who envisaged the use of powerful searchlights to probe the atmosphere. Indeed, LiDAR has since been used extensively for atmospheric research and meteorology. LiDAR instruments fitted to aircraft and satellites carry out surveying and mapping, a recent example being the U.S. Geological Survey Experimental Advanced Airborne Research LiDAR. NASA has identified LiDAR as a key technology for enabling autonomous precision-safe landing of future robotic and crewed lunar landing vehicles. Wavelengths vary to suit the target, from about 10 micrometers, infrared, to approximately 250 nanometers, UV. Typically, light is reflected via backscattering, as opposed to pure reflection one might find with a mirror. Different types of scattering are used for different LiDAR applications, most commonly Rayleigh scattering, Mie scattering, Raman scattering, and fluorescence. Suitable combinations of wavelengths can allow for remote mapping of atmospheric contents by identifying wavelength-dependent changes in the intensity of the returned signal. The name photonic radar is sometimes used to mean visible spectrum rangefinding like LiDAR, although photonic radar more strictly refers to radio frequency rangefinding using photonics components. Design. The two kinds of LiDAR detection schemes are incoherent or direct energy detection, which principally measures amplitude changes of the reflected light, and coherent detection, best for measuring Doppler shifts, or changes in the phase of the reflected light. Coherent systems generally use optical heterodyne detection. This is more sensitive than direct detection and allows them to operate at much lower power, but requires more complex transceivers. Both types employ pulse models, either micropulse or high energy. Micropulse systems utilize intermittent bursts of energy. They developed as a result of ever-increasing computer power, combined with advances in laser technology. They use considerably less energy in the laser, typically on the order of 1 microjoule, and are often eye-safe, meaning they can be used without safety precautions. High-power systems are common in atmospheric research, where they are widely used for measuring atmospheric parameters, the height, layering, and densities of clouds, cloud particle properties, extinction coefficient, backscatter coefficient, depolarization, temperature, pressure, wind, humidity, and trace gas concentration, ozone, methane, nitrous oxide, etc. Components. LiDAR systems consist of several major components. Laser. 600 to 1000 nanometers lasers are most common for non-scientific applications. The maximum power of the laser is limited, or an automatic shut-off system that turns the laser off at specific altitudes is used in order to make it eye-safe for the people on the ground. One common alternative, 1550 nanometers lasers, are eye-safe at relatively high power levels since this wavelength is not strongly absorbed by the eye, but the detector technology is less advanced and so these wavelengths are generally used at longer ranges with lower accuracies. They are also used for military applications because 1550 nanometers is not visible in night vision goggles, unlike the shorter 1000 nanometers infrared laser. Phased arrays. A phased array can illuminate any direction by using a microscopic array of individual antennas. Controlling the timing, phase, of each antenna steers a cohesive signal in a specific direction. Phased arrays have been used in radar since the 1950s. The same technique can be used with light. On the order of 1 million optical antennas are used to see a radiation pattern of a certain size in a certain direction. Scanner and optics. Image development speed is affected by the speed at which they are scanned. Options to scan the azimuth and elevation include dual oscillating plane mirrors, a combination with a polygon mirror, and a dual-axis scanner. Optic choices affect the angular resolution and range that can be detected. A whole mirror or a beam splitter are options to collect a return signal. Photodetector and receiver electronics. Two main photodetector technologies are used in LiDAR: solid-state photodetectors, such as silicon avalanche photodiodes, or photomultipliers. The sensitivity of the receiver is another parameter that has to be balanced in a LiDAR design. Position and navigation systems. LiDAR sensors mounted on mobile platforms such as airplanes or satellites require instrumentation to determine the absolute position and orientation of the sensor. Such devices generally include a global positioning system receiver and an inertial measurement unit, IMU. Sensor. LiDAR uses active sensors that supply their own illumination source. The energy source hits objects and the reflected energy is detected and measured by sensors. Distance to the object is determined by recording the time between transmitted and backscattered pulses and by using the speed of light to calculate the distance traveled. Flash LiDAR allows for 3D imaging because of the camera's ability to emit a larger flash and sense the spatial relationships and dimensions of the area of interest with the returned energy. This allows for more accurate imaging because the captured frames do not need to be stitched together, and the system is not sensitive to platform motion res. Thank you for being with us until the end of the program. Be sure to mention your opinions about the educational video in the comments section.